Well, welcome everybody to Unleashing STEM Potential Data Tasks that can empower every learner. We are the Chem Adventures. We adopted that come with small room. Adopted that name because we assemble when needed to help tackle some of these problems and help assist students in learning. Can you go to the next slide?
Yeah.
But you're not druggies, right?
But we're not druggies. We get that every time we talk about being chemists. People want to know if we can make meth. We can. It's not that hard, I think, to make that open in your bathroom. But so I'm from Bustos-Works, and I'm from Cal Poly Humboldt. This is Cory Antonakos from Diablo Valley College, and Paul Daubenmire from College of Marin. And we are an intersegmental team of educators. We are all chemists. Some of our members are not here today, but we're representing community colleges, and we're representing the CSU, and we're representing the UC. So some of the motivation for our work is really to redefine smartness and belonging in STEM and bring in all students. And this is a quote from a student at Berkeley, student at Berkeley, that really kind of captures some of the things, some of the feelings sometimes students have in STEM classes, not necessarily just chemistry, but STEM classes in general, where this is after a midterm exam, getting a grade back where they didn't feel that they belonged in science, that they weren't smart enough to be part of science. And so these are some of the things that we want to disrupt, these narratives. We've also have some quotes here from faculty. And these are some of the other things that we want to disrupt. And these are, you'll see some similar trends here, some similar themes where we have faculty saying that students don't deserve to be in our institutes of higher learning, where they are saying, pushing back that students are failing. So, and this is something that has happened in chemistry for a long time. You know, if you got this exam back and you didn't do well, maybe this isn't the class for you, maybe you don't belong there, right? You're not doing well. And also some of the things that we'll hear is like, our students don't know how to do math. They don't know this. Can you believe this? They can't write. They can't do math. And so these are some of the narratives that we're trying to push back against. And so these messages about smartness can exclude students, and we want to be as inclusive as possible. So these are some of the things that we're trying to disrupt. These narratives about what is smart, who counts, right? Is it especially in math and science? No, I'm a math person, or I can't do the bill, I'm not a math person, somebody else there, right? These messages seem to be built on like there's an innate talent, and you know a lot of information, you're really quick to answer questions. And these can be very problematic, right? And exclude students from wanting to be STEM majors. And they also have both racial and genderized perceived abilities, which could put, white and Asian males above our Black and brown students and female students. And then often our gender non-binary students don't even see themselves in these equations. And so again, we want to disrupt what counts as being smart. And you'll notice when we get into the activity, you'll have a little sheet there about smart things to do. And I think this also, and who count, and this also goes to some of the points that were made at today's panel, in the first panel. And so when we think about learning as a community, right, and everybody being involved and kind of disrupting some of those hierarchies that are in the room, I think we talk about that a lot in some of the work that we're doing when we're trying to create a community of learners and disrupt some of these narratives. And this also plays into how we do science, right? We do science in groups as scientists. And so how we practice science and how we teach science are not with each other. So
speaking of doing science in groups.
Can we rearrange the activity? We'll rearrange you when we start the activity too. So science as a practice is, when we're developing and explaining models and sets of practices, these things are iterative and they're messy and we make mistakes. but we teach science sometimes in the classroom as if this is a discrete body, a static body of knowledge that you memorize. And we talked about that, I think, in some of the opening panels and sessions, right? What is this delivery of knowledge? And really, when we're looking at these data tasks, this is more about everybody having the knowledge and looking at data and being a community of learners to make sense of this data to create models and ways of thinking. And so one of the things we talk about a lot too that came up in the panel, I think Michael said this about being a coach, right? I often think about that when I'm teaching science, right? How are we in this together, and how am I really facilitating this learning as a community to move students forward in thinking about science? So one of the ways we approach this is really to think about these big questions. So when we're supporting the new meaning of who counts and what counts in science, and we're developing our students as scientific thinkers, we're thinking around these big questions. So we want to support rich learning at a certain pace that achieves established learning outcomes. This is a little bit of a struggle for us sometimes in the sciences, because we'll get pushback if, you know, we have a certain amount of content to cover, a certain number of student learning outcomes so that students can get from one class to the next. And so we've really tried to take all of those things into consideration to get through those pieces, but develop our students as scientific thinkers and really shift that meaning of what counts and who counts. Okay, so what we're going to talk about next and what we're going to engage in, and a lot of work that we've been doing, is really developing what we call group-worthy data tasks. And so this invites the students in on these big sets of questions. And so the one that we're going to talk about today in this big question is, why do solutions conduct some solutions conduct electricity and others do not? So that's the big question that you're going to wrestle with today. And we're going to have multiple entry points by giving you different forms of data. What you'll see in this picture here are 3 pieces of data in different forms. And the reason that this is important is because we want you to all have multiple entry points to be able to get into this problem and start to think about it as a community of learners. And hopefully there's places where different people will hook onto different sets of information. So for example, you might look at the picture and be like, okay, this is a piece of data. I've got a solution here of sodium chloride and the light bulb lights up. That's a piece of data, right? What do I do with that data? And somebody else might look at this pictorial representation, this kind of cartoon representation that has some information that might resonate with them. Or you might want to look at data in this tabular form, some multiple points of entry in order to talk about this problem and think together about what it means to be a competent scientific thinker. And all of these are grounded. This is one activity that we have of several that we have developed to really ground in the natural world of being able to solve these problems. And I'm going to turn it over to Cory. One other thing I want to say, maybe you can take this over, is really thinking about the transparency piece and bringing students into that trustworthy piece, which was mentioned today at the panel too.
Yeah. I think what Carmen's kind of talking about is right. This whole sort of curricular tool design is about sort of breaking down those barriers, those hierarchies between the instructor and the student, right? They talked this morning about like students can be the teachers and instructors can be the teachers. We can all teach each other, and that's what you're all going to do. How many of you are chemists, have a chemistry background? I love it. It was great. I hope what we're going to show you is that with no chemistry background, you can approach this, because the whole point of these group-worthy data tasks is that they're going to show you that you already have skills that are applicable to chemistry, whether or not you know the lingo or whether or not you've taken a chemistry course recently. Because most of our students come in being like, well, I'm afraid of chemistry. I don't know science. I'm not a science person, not a math person. And we're here to be like, those aren't real things. Like this is what science is about. So we're going to do a data task, right? Like Carmen kind of explained, these are the pieces that go into it, but it doesn't quite resonate until you actually engage in the work. So we're going to do the task with your group, and we're going to reflect on sort of what you just experienced, how you saw those design principles, and how you sort of experienced different ways of really being smart. So, Paul, if you could. All right. So I'm going to give you a few slides to kind of jump you off, but before that, I'm going to just orient you to what you have in front of you. So we want to do this in about groups of 4, and I think we have probably the right number. So maybe everyone should get to a table first, and then I'll introduce it. If we could get 8 people around each table.
So there's 4 more people at this table in the front.
7. Yeah, actually, those, if you in the back want to come to this front table, that would be perfect.
Yeah, and then we'll have 2 groups of one will be another introduction.
Yeah.
Yeah, we'll go to this table.
Cool.
We'll do that. Those things are true.
Do you want to sit down?
You want to join the group of 4? I think we're here.
Yeah, you can be at this table, Danae, right?
Either way.
Yeah, so basically we can have like a group of 3, a group of 4, sound good? Yeah, and then we'll cut this table down the middle, group of 3, group of 3. And then the back table, a group of 4 and a group of 3, sound good? All right, cool. What you have in front of you, I'm gonna talk about a little bit more, but you all have a text card. There's only 1 per group. This is intentional and by design. You all have a note sheet, also 1 per group, intentional and by design, right? Notice no one's allowed to just sit here and do the task by themselves. We're forcing you to collaborate. You also have this data and information sheet. You won't necessarily need this, but because I'm going to walk you through some parts of the task because you don't have a whole hour and a half to do it like I like to let my students have to do it. Maybe not an hour and a half, maybe like an hour. You're going to have like 20 minutes, so I'm just going to focus you on one part of the task. So this part you probably won't need much, but it's there for your reference. And then you also have this bag of cards, and you are going to be needing those. So that's what you have in front of you. Oh, yes, to go back to this one. So this data task is about electrolytes. It's what plants crave. I don't know that reference. My students don't get that reference. They have not seen that movie. Your task, so your team is going to use these particulate views of solutions cards. That's the cards you have in front of you. That's going to be sort of the main part of the task. To write a rule that accounts for how strongly a solution will conduct electricity at the molecular level. So in chemistry, we really like to talk about using atomic scale explanations for macro scale observations, right? So at the macro scale, we see light bulbs light up. We see electricity being conducted. At the atomic scale, what's going on? How can we explain that? Excellent. So on your task card, if one person in your group can just kind of see, this part says examine particulate views of solutions. Really parts 1 and 2, I'm going to walk you through in the next 2 slides. So parts 1 and 2 is what I'm going to introduce on the slides. We'll do group part 3 as a whole class, and then you'll do basically part 4, and then the back together in your group. So one thing just to make you aware of is that the solvent is water for all of the solutions that you're looking at when you're looking at these cards. This green box, you can assume the green is like the background and it's water. Sometimes it's a yellow box, sometimes it's the blue box, that doesn't matter, but the solvent is water. So this is like a cup of water with some stuff dissolved in it. You might, for example, see sodium chloride dissolved in it. Sodium chloride is table salt. It's the stuff you put on your French fries. Or you might see sugar dissolved in it. It's the stuff you put in your coffee to make it sweet. And when we dissolve sodium chloride in water, it does something interesting. It dissociates into sodium and chlorine, and they're separate ions. When we dissolve sugar into water, that doesn't happen. A sugar molecule stays intact. We don't have separation of those particles. So that's an important distinction that you might want to keep in mind as you engage in this task. Next slide, please. We also, if you've been taking this class, we've talked about concentration. Right? So you all know what concentration means. So I'm going to remind you, concentration just means the amount of particles in a solution that fit in a given amount of volume. And we can assume that each square represents the same volume. So within a given volume, a high concentration means there's lots of particles. A low concentration means there's not a lot of particles. That's what it looks like in the picture. You also might notice the number on top, as you can see where it says like solution 6.010 big M NaCl. that's a number that's actually telling you a concentration as well. So you can see 0.010 is a higher number than 0.005 is a higher number than 0.003. So those numbers are also telling you high concentration, low concentration, noticing that there's data represented in different ways here. Thanks. So kind of what I was just explaining, there's a lot of information on these cards, right? And this task is intentionally designed so that no one of you has all the skills needed to succeed, but all of you have some of the skills. And that's why you're working in teams. This really requires multiple brains. So if you look at all this data and you're like, this is too much for me to digest, that's good because you have your teammates. You digest one piece of data, your teammate digests another piece of data, talk about it, come together to just figure some stuff out. Last note, there's like numbers on the flask. So it's the 12 and the 5, and it says like solution 12, solution 5. Those don't mean anything. Ignore the numbers. Those are artifacts from other data tasks, but they're not relevant for this one.
Do you know how to cue the video?
Yeah, he embedded it into the slide. So questions before moving forward. How's everyone doing? We're okay.
Chemistry escapes like a sweater.
Yeah, that's we're closing the door. You can't get out here. All right. So what we are going to do as a whole class is we're going to collect some data from this video. So if you can pull out the note sheet, if you have in front of you, if you're like the lucky one in your team that has this thing labeled note sheet, select someone. And we're going to watch a video and have a pen. So everyone have, there should be a table on the back of it.
Okay, hand goes down. Or hand.
We're looking for it.
Oh.
That's one sheet.
If it just.
Yeah,
Switch it out. Did anybody else get a blank one on the back of your tab?
yeah. Does everyone else have something with a table?
Don't have it.
Oh, no. You don't need one? You get them? That's okay. Everyone has something with a table now? Yeah.
Okay, I got one.
You guys, science is messy. Big. So what we're gonna fill out is if you see the column where it says light bulb bright, dim, or off,
Okay.
that's what we're gonna fill out while we watch this video. This person is going to show different substances and whether they make the light bulb bright, dim, or off. So if you can record as you see what's happening, that's going to be helpful. Sound good? If you miss things, that's okay. I have the answer, so I'm sure. Students usually have more time for this, but I will let you work.
All right, here we go.
Oh, hi! Today we're going to learn about solutions and how they conduct electricity, or don't. Tap water. Distilled water. Huh? What? Salt water, 1 teaspoon per cup. Hydrochloric acid, nice. Sodium hydroxide, ooh, just as concentrated. Sugar water, sweet. Vinegar, a weak acid. Ethanol, a dissociative that doesn't dissociate. Don't try this at home. Barium sulfate. It's insoluble. No conductivity here.
All right. Oh, those, yeah, these videos exist. Yeah. Cool. So hopefully you got some of that data down. I'll walk around, and if you missed any pieces, we'll fill in your table for you. But if you can go on the next slide, Paul. Cool. So if you're like, well, what should I be doing this task? I don't know any chemistry. How can I possibly bring skills to the table? These are smart things that you can do. You can interpret symbolic and visual representations of solutions. That's what you're going to be looking at. You can recognize patterns and relationships in data. Science is all about recognizing patterns in whatever form you want to look at them in. Determine which variables are most important, right? There's kind of a lot of data on those cards. What do you think is really relevant here? Keeping track of amounts, there's a quantitative aspect to this. Imagine how changes at the atomic level would translate to these macroscopic observations, like what's causing the light bulb to light up or not. Wonder aloud about what you're noticing, right? Even if those first ones feel like, oh, those are even hard skills. Wonder aloud, feel like, I don't know, I noticed this. What do you all think? And ask questions about the data that's in front of you. These are the skills that we're going to be, that we're looking for. So as I said, we're really going to start, right? So we just did number 3 on the task card. We're really going to start at number 4. And then we're going to try to get through number 4. And then on the back, this bringing it together. So what you're going to do is, whoever on your team has the task card, read the instructions aloud to your group. And then you're going to put your answers on the note sheet. And you'll see on the note sheet, there's a corresponding number 4, and then I'm bringing it together. And you're just going to fill those cards out. Sound good? Go ahead and get started.
They need that last.
The note sheet is 2.
Well, I guess if we don't necessarily need this if we just have them. Because
You're gonna write a rule. The one is okay. If they can answer this, that's really awesome. It's writing down.
We're giving them the experience of that.
Right, yeah.
We're not assessing them.
Yeah.
Okay.
Thanks for bringing that up.
Sorry. No, we're like, why is the sound so different?
Thanks for bringing my.
Oh, no problem. Sorry.
And then, we also have distilled water off.
I just read it.
I'm not really, yeah, so they solved, right?
Yes. So,
Why it's like.
we're up. Oh, wait.
These are just extra.
Very hard to say this. Yeah. And we're guessing is all in the word.
Maybe I can point you to the patterns.
Oh, that's not the same problem. Yeah. Okay. So now from the end. Yeah, I mean, the we have some other ones. I mean, we're just matching. What are the observations? Yeah. We didn't do. I'm just trying to see like. These 3 are. These 3 are all very simple. That was the last right for, yeah, like it was still pretty bright. I remember thinking like, yeah. Yeah, no, I mean, I just, so that I got.
You watched the video? The video is on the QR code on your, one of your pages.
I knew that I came on this phone, but all I'm saying is like going really. It's not just saying, it's not a bit. What is that meaning? How much they resolve or separate. So I'm gonna go this, yeah. That's basically like the fun that I saw in Instagram. We got that right there. I think I feel like these three. So.
Yeah, well, I just kind of moved these in, but we didn't actually see that in the experience.
No, I mean,
English one names be
let's go back. Come on, so we can go.
Yeah, so I'm gonna say that sufferers So we want to stamp them by how conducted it's going to be. So I think these are going to be the same. They all have the same structure and they all have some demonstration. When you go to the hydroform, those are free.
Okay, that's an electronic.
Right. Okay, and then the vinegar, I think.
We all did the same thing.
It's this.
They're gonna take this, we're gonna put this in order, right? This is
I have this.
my guess is.
You know, I probably some of the break up.
I just would like
That was too big.
That one breaks up.
on the right now.
These break up one.
Even like this might be right.
Breaks up
Yeah.
three.
I think we have one call. This one went out there.
All these light bulbs are going off. We're thinking about.
Sure.
Anything else? Okay. You think all these are? Just according to.
This one's way right.
The shade of that's the color.
This one's.
Yeah, let's. Right?
I really.
Maybe, I don't know, anything else in reverse?
And the noise.
So they're all
Yeah.
Video that show.
Right. These are polite.
We can all show them, so we're getting paid. Is it a job? It's a job right off your body.
Discussion. Normally, students would have like 45 minutes to an hour to do the whole thing. We're just trying to give you a little piece so you get the gist of it. But so if I'm still the teacher and I'm still kind of wrapping up this task, one thing I would do is I would point out a lot of smart things that I heard, and I tried to record them on the board. Someone said, "How do you know it's ionic?" They were asking some good questions of their teammates. Their teammates said, "Well, the two elements break apart, so you see circles and squares." They were really explaining, this is what I'm looking at in the data. This is how I'm connecting it to this word ionic. Someone pointed out it's the number that breaks up. So they said this one breaks up into 1, this one breaks up into 2, this one breaks up into 3. That was very astute observations. Someone said, I guess these have multiple ions, but these don't, sort of noticing things that dissociate, things that don't. We had some good like hand gestures to describe bonding, right? A lot of chemistry is like, how do I explain this? It sticks together, it doesn't. Someone said these were bright, so it makes sense that the ionic ones were the bright ones. We're kind of converging in on this. Someone says, what does ionic mean? These are good questions, right? If we're using lingo that your teammates don't know, it's important to define that, right? The idea is we're moving away from this idea that chemistry is just using fancy chemistry words, right? It's actually being able to explain what you mean by those words. And then we got like half of a sentence, the higher the concentration, someone started to find a pattern with concentration was doing something. So we heard lots of good, smart things. If you want the like, punchline of it, it's really the concentration of the dissociated ions, right, that makes something brighter. So it's not just the concentration, it's not just whether it dissociates, it's how many ions are actually in there in a dissociated form. So I'm gonna pass it over to Cory.
Okay, so the next slide, we're gonna take our student hat off and put back on our inspired convening participant hat. And in your little group, ask this question: what feature of this task allowed you or your group members to demonstrate being smart? So if you could pull that slide back up, Cory.
Yeah.
So the question is, what of those things were allowed to be manifested through this activity? So in your little group of 3 or 4, we'll give you a minute or two to just discuss that. Did some of these come up in your group?
Yeah.
And if so, what or why? So the room can start buzzing again.
Definitely has Travis.
We don't know the answer to this.
Well, the thing
Before we put
It became this writer Okay, so just because of timing, I'm gonna bring us back together and maybe one group, I know there's two, one group per table, there's 2 groups per table. There could be one bold volunteer, I don't know names, otherwise I'd call on you, who would just share out one smart thing that you talked about in your group. So maybe someone at this table? Go ahead. Wonder aloud? Yeah, I heard a lot of that. There's a lot of self-admitted non-chemists and a lot of wondering aloud as to how these things are helping us make sense of these patterns. Thank you. How about in this group?
Recognizing patterns?
Right on. So Cory identified this as the beginning. We talked about these themes. We're preparing folks to go out and just look at information. How do we pull out meaningful trends or patterns? And then here?
We asked questions about the data. We didn't know if our data was correct.
Yeah, right there. How many of you all know something before you sign up for the class? That's why you sign up for the class. You don't know what you don't know, and that's where we want students to be able to walk in and safely do that. One more
I was
time.
going to play off of that. Amongst my peers here that we're all learning this together, it was safe to just say something and just put it out there and not have an answer and not expect anybody else to know either. That's okay.
Very good. So maybe we can go 2 slides ahead to that. So our work is based off of a theory called complex instruction, which is actually generalizable across not just science domains. It began in the humanities with some work at Stanford. And just a contrast between our traditional one-dimensional instruction, which typically has a right answer, typically involves all the students doing the same skill. It often manifests in who finishes fastest. And then it allows students to begin to self-disaggregate themselves as to who knows it and who doesn't. And I heard the group here say, let's see who took chemistry last, right? They're already in that realm. Let's go compare who was here last. And therefore, these labels of smart in science or not smart in science naturally get assigned by students, self-propagated, and if we as faculty were taught that way, we come in and we propagate those labels. In contrast, the group-worthy tasks bring out authentic problems, and we'll talk about the design of these in just a second. Multiple intellectual abilities were needed at the table and even welcomed because there was way more information than one person could really kind of own or make sense of. And therefore, as more students contributed, there was more recognition of each one's competence to be a scientific thinker or learner. And so when a teacher publicly recognizes that, those status problems just begin to go away. And we'll see some data later on. So we're breaking down these traditional definitions of what it means to be good in a science. Next slide. So part of the challenge to us as instructors or curriculum designers is, one, how do you create a data task? You notice this was curated in such a way that there was very kind of funneled patterns or conclusions that you could make of it. And so we spent a lot of time sitting and trying to design data tasks that are not too open-ended, that go in so many directions. You can imagine this working out in a history class or a sociology class to explain a reason for a war or for some kind of conflict, right, with multiple strands. But what we wanted to do was get this topic that's discussion worthy turned into a question, allow a way for videos, manipulatives, numbers, tables to all play a role. And then again, allow students to see patterns, to generalize those patterns, and even to apply or predict. In a sense, we could have dropped a new card for you based off of what you've just learned in 15 minutes, and you could begin to say, that is going to behave like this, because I now understand the pattern there. And so let's just go back to our design principles for a second. Again, the big question with multiple entry points, and then this accountability to thinking together. You notice as an instructor, I'm not sitting back. I have a way to be right in there in the classroom. I can gauge who is participating. I can gauge the types of questions. I can even draw out ones who are a little bit less active. Over the course of a semester, you're really breaking down these status differences. And then everyone is elevated to see themselves as a competent scientific thinker. And then guess what? Next time you're out in lab or even at the coffee shop, what are you thinking about? Dissociating or dissolving, right? It doesn't go away. It sticks with you. I have so many students who come back and they're like, I was just Netflix binging and I couldn't stop thinking about this, right? That topic that they talked about because it showed up in their real world. Next slide. So some of the themes that we've begun to take from this work, we were one of the original grantees with the Learning Lab. And through our scaling grant, we began to identify collaboration, intellectual courage, making connections, and diligent skepticism as themes that kind of emerged from this type of observation. And I just kind of wanted to point out, as there's too much to scan, of course, these slides are online, but wanted to point out some of the ways in which you were rewarded for being scientific without even knowing it, right? Giving a way to reticulate other people's thinking in your own words. And so just the act of verbalizing, we know, causes a part of the brain to engage that is more than just passively reading it with your eyes. Intellectual courage, thinking out loud. And that right there for an English language learner is a barrier already. What is not spoken in chemistry, we're often translating between English and chemistry English. There's a language translation there. So if you're asking someone to do another translation, we have to allow time and recognize that's actually an additional skill set they're bringing, the ability to translate twice some information. And so to make that translation and then be bold enough to verbalize it, it's much easier to do that in a group of 3 than a lecture hall of 30 or 1,000, right? Then making connections with material is often really all we're doing. If you go to any chemistry class, I think any faculty would point out that is their goal. You can see that explicitly happening, kind of like you can see neurons form when you do a brain scan, you can see those axons and dendrites connect. That's literally happening with light bulbs. I was watching your light bulbs go on here. And then finally, this, as you get more comfortable, 1, with your group members, and 2, with the material, you can be a skeptic, where someone proposes something and you have a way to push back a little and say, and that was happening in a group over there. They were looking at circles and trying to identify what the circle meant. And there could be a little bit of a back and forth that would not have been there if I was just here at the board drawing circles on. So this opens up a way for real scientific thinking and learning principles to come out. And that's that. So we just wanted to share a little bit of output and outcomes we had. We collected over multiple semesters what we called student reflection papers. So students are chronicling or writing end of semester papers showing we analyzed, we coded and analyzed their thoughts. And what we saw was a lot of shifting away from lack of confidence, lack of self-belief in themselves and in their status as scientists, moving away from this realm of, I don't understand this, it doesn't make sense to me, into this, and also away from this realm of chemistry as math. I was just in a presentation there that kind of disambiguated those two things, but that's often the association we have. I'm not good at math, I am not going to be good in science. Why? As we heard this morning, sometimes math is the gateway class that prevents folks from going further into science. So we saw shifts actively away from those themes into the next slide, shifts toward a belief that anyone can do science. If you're sitting in a group with name the demographic and you are improving and they are improving week by week by week, your belief about who can do this is just going through the roof. And we see that seeing yourself as capable. So the self-confidence that developed, those narratives, the status hierarchies we began the presentation with, began to be leveled out. We have some data there. And then really this idea of intellectual risk-taking. How did we come up with vaccines in such a short time, right? There was some intellectual risk being taken right there to say, we have 30 years of data, let's propose this as a solution and look what science was able to do in 6 months. So how do we begin to reward those skills early on, cause students to value that before they have to go through 10 years of education? Not till you're a PhD are you allowed to take intellectual risks, right? It's a little backwards. But if we can sow that seed early on, that gives them the way every problem set they do, every lab exploration they do. And I'm saying they, just me, right? Yourself in that same scenario. These were the shifts that we were seeing with our students. So this quote especially, I like, offering my ideas even when they were wrong, because you can learn so much from a wrong answer, sometimes more than the right answer, and bouncing back from setbacks. And so these were different trends and factors that we measured. So maybe the next slide, Cory. So this is some data from a community college instructor, the same instructor teaching the same content, but pre-data tasks, so traditional instruction in orange, and then post-data task instruction in blue. And you can see the instructor, has a level of success. It's also disaggregated, so there's a lot of factors here, but it's disaggregated by various demographics that we traditionally would consider underserved or underrepresented in sciences. And you notice the instructor is effective. There is some, let's say it this way, before data tasks, here's kind of our average. But notice the gains made after data tasks from these groups here, bringing to near average. And here's all our students. So it's not this thought, we'll just say that the gaps were narrowed and we're seeing improvement in populations that we want to add value to. So this again is from one class. Next slide, maybe we can point out, this was in a publication after the work of our first grant, where we went back and looked at 3 semesters. And here we actually saw a reverse equity gap, where we saw our underserved students actually have greater gains right there in their GPA as a result of working with data tasks than from before. And so we, again, published that. That's available through the link, but we're pretty confident that this method, and as you all experienced, is a way through your own design, through your own experience, is something that can be incrementally added into a classroom. This is not a entire curriculum overhaul, but you can envision how you could take one unit in your course or in one of your departments and just say, let's try this, get a group of faculty together. And we actually ran an institute 1.5 years ago where that happened. 25 faculty came in from other campuses. And as a result, data tasks are now sprinkled throughout community colleges, not just in chemistry, but in other science domains.
Yeah, and physics, biology, people are trying it. Also, note this is from a CSU. The previous data was a community college. See a different level.
Carmen, if you want to add, it's even spreading to the humanities a little bit, this kind of thinking, and I don't have a slide on that, but okay, so let's just walk away kind of with some take homes from this, that we often have this belief in our disciplines. There's this narrow set of things you got to know before you can move on, things you are able to do before you can be stamped as part of the academy. And that's actually, once you're in the profession, you do a very different set of things than what you had to do to get into that route. So we want to help students recognize that, develop those skills that they already have, but have kind of been set aside till later, bring those out real time. All of this is actually an introductory chemistry curriculum. This is for students with no background whatsoever. At the community college, our former chancellor's quote was, "We accept the top 100% of all students." So that means everybody walks in and needs to have an entry point to an activity like this. Then we're proposing that Chem Avengers have been pushing on this, but we need to shift our pedagogy to reflect this messiness and reflect the complexity of learning and reward that along the way. So that's not always easy. We've made some data tasks that kind of don't work out well, so we've gone back, but eventually we get some group-worthy data tasks that have met our design principles, allow these scientific thinking and learning practices to come out. And I would even throw in, allow folks to develop academic language proficiency, which we see as a boost to our language learners in this state. So final slide, I believe, yeah, is we're happy to answer any questions. Again, there's a team of 9 of us that have been working throughout the Greater Bay Area and North. If you're interested in getting the whole set of this curriculum through Canvas Commons, you can link into Chem Avengers through that search, and you could import that into your Canvas course. We now have a chemavengers.com link, which redirects to that, no login needed. So a classroom could literally go in and just do the data task through that link. Again, there's an email there where you can reach us at, and maybe we can pause for questions.
You didn't ask us to make a prediction at the beginning of this whole experience, and I'm guessing that was a conscious decision, and I'm curious if you could talk about that.
Yeah, I mean, I think that is maybe part of some data tasks. I'm trying to think, but it's not necessarily the core. It's not like the main piece of the data task to like go back and see if your prediction is right. It's more about, here's some data, find a pattern in that data, and then make your prediction based on the rule that you made from that pattern. Does that make sense? So I think the predictions usually show up more at the bringing it together part. It's like, now apply your rule to come up with something. Yeah, but that's something to think about to kind of structure it a little bit better, to start it with the prediction.
Yeah, you're talking about the mistake or like design things that you didn't do that didn't work so well. So what are some of the things that you learned along the way? So as we try to do this, we could be like, oh, maybe we should try to avoid that thing, or anything else that you learned as you're.
I do feel like the idea of something being group worthy is hard to achieve. That that if you make a task that really doesn't have multiple entry points, or that has a kind of an obvious answer, then you might get that student that's taken chemistry before that's just like, let's jump to the end, I know the answer. And so I think designing them with enough data and enough messiness helps alleviate that, because I've had students that even say like, oh, I thought my friend was super smart, but even they struggled on this one, so it's something that really levels the playing field if you have enough complexity in the task.
Really working away from that worksheet type of just going down and drilling down to the answers, even if you're like trying to do that worksheet and scaffold that work. So those are things that we're trying to get away from. And again, going like it is taking us a long time, like what's really
Go in the back and then we'll circle around. Go ahead.
I know I have my own opinions of the answer to this question, but I get skeptics asking me often, well, this is great, but the time that you take to do these activities, you could be teaching so much more material.
content.
How would you respond as people who've done this? How would you answer that? Because that's the common purpose.
So
I would say you can't. I disagree. I'd say that that what you learn, what you just learned in 15 minutes, if I spent that time lecturing, you might learn nothing from me lecturing, right? Like, I think it's this misconception that if we put something on the board, students have learned it. And if we realize that that's not always true, then we realize that this actually gets them a lot farther.
And I think goes back to some of the things that went on the panel today, right? Like content is everywhere. It's cheap. There's videos. We can find other ways to deliver that content. But we can't find these other ways to sit together and make sense of the content, to solve scientific problems and scientists.
There's also, sorry, one more thought that like, there's times, especially actually in this data task, it's come out where we think a student knows something and they don't. Like we have a nice video of Erin teaching. She's another one of our teammates. And she comes into like the breakout room, this is during COVID on Zoom. And she's like, well, what do you think? And they said, well, we think when there's a higher concentration of ions, the light bulb is brighter. And that's correct, right? They said something correct, but she didn't validate their answer. She said, okay, can you explain how the data supports that? And she found out in that they were only counting the red circles as ions. So she's like, they made a correct statement, but they actually don't understand. And without this opportunity, she wouldn't have learned that about her students, and she wouldn't have been able to correct that. So that's another piece of this.
And I'll say, a theme talked about this morning is converting the role of the faculty from just a content deliverer to a knowledge creator. When a faculty member is interacting with students at that level, you can see and hear misconceptions or alternate ideas and can adjust them real time. And so the student doesn't leave the classroom with this wrong concept that gets propagated down the line. The question is, can you do that with all 24 students? We have the luxury of that approximate class size. You have to train your graduate students, right, to be into this kind of ability to interface. But what I found is students welcome that. Students want that interaction because, as Carmen mentioned, they can get the content other places. They can pause it, rewatch it, subtitle it, right? All their particular needs. So we are adding value to the instructor's role.
And I just want to say one other thing that came up is like getting rid of grades, right? So that assessment for that student got the right answer, maybe got an A, but then we walked away with misconception. That's not going to serve them well later.
There's a row of hands here and we have maybe 3 minutes.
I was gonna say, there's something also to be said about sort of interpersonally, how we as faculty correct students.
Yeah.
Right? It's important to guide them, but there's ways that we can be more harmful than we judge them.
Yeah.
And so I think just highlighting that too, or have you, because when I have a student who may be wrong, it's like, I don't say, no, that's wrong. I say, that's actually really good, but that's not necessarily, what we're looking at, but that's a really good idea. So sort of that positive reinforcement, I think really helps. And that's something that we don't necessarily do as faculty.
Yeah, and then we'll end. Go ahead.
I was curious how much, this was part like presentation for fellow educators and then also a demo of what you do in the class, but I'm wondering how much you tell students about the like meta level about why you're doing it this way.
I tell them, I'm like very transparent about it, because a lot of them are like, like, what are we doing, Dr.
Right.
Antonakos? You know, they're like, why aren't you just like putting information on the board and asking me to like do some math? And so I don't know, I kind of tell them, I say, well, but when you actually go out into the real world and if you, whether you do chemistry or whether you become like a nurse or work in healthcare or whatever you do, these skills are really what's valuable and they're actually what scientists are doing. And it does like allow for more exploration, right? I have students asking questions that I don't always know the answer to. And I'm like, oh, well, how might we approach that? You know, like, let's be scientists here.
I get the occasional student who self-selects out of that environment and wants to be in a lecture class.
Yeah.
Right?
Yeah.
And I'm like, well, then that will suit you better. So that's fine. That's why we have options. Yeah, Stan?
I was just thinking while doing the activity, how fun it would be in a wet chemistry setting to like mix in actual salt and,
Right.
you know, stick the probe in.
Yeah.
So I'm wondering, like, how do you make those decisions when you're designing the activity? Whether it's in lab or in lecture, whether it's physical cards or digital tools?
The original mandate of the learning lab was to develop online curriculum. And so we steered it in that direction, and then the pandemic gave us a kick in the pants further in that direction.
Sure.
But one of our colleagues at Sonoma State actually did begin to pioneer in a wet lab in that direction. So it's very doable. And that's what students are always asking. They don't want the cookbook lab. They want to say, can I add these things together, right? And I'm like, no, it's not on the worksheet, so don't do it. So that's the direction that has a lot of room to grow.
And I'm just adding that demos, right? So we'll often do demos at the front of the class, and this would allow a great opportunity to slow down with those demos and have the students collect that data in real time. And when I first started, when I was on stage, I had a colleague who was like, you do all these demos, but then I put it on the exam and you never get the right answer. And so it's because they were doing the ooh and ah, it was fun, but they weren't doing the data collection of thinking, the making sense of it. There wasn't space in that classroom. I think it can involve.
Great presentation. I really like your presentation. It worked really good. But I have one question for you. If I stick my pocket knife in an electrical light, will I light up?
Well, how might we explain that? You should be able to pick a bath in that ultra filtered water, that DI water, and throw your TV in there.
And then when it's smoother.
You won't get electrocuted.
I'll try that.
Here.